Hi students, in today's video we'll discuss about the structural activity relationship of penicillin. As we know that penicillins are a class of beta-lactam antibiotics which is widely used to treat several bacterial infections. So the Alexander Fleming in the year 1928 he discovered the penicillin, and here I have displayed the structure of penicillin. So mainly the structure has a much influence on the stability of the drug molecule as well as to the stability in the gastrointestinal tract and the susceptibility to the bacterial metabolism. So here, in case of penicillin, the core structure of penicillin consists of a bicyclic system. Here you can see a beta-lactam ring and a thiazolidine ring structure, and this forms a bicyclic system, which is called as a pinum nucleus. So this contains a beta-lactam ring and a thiazolidine ring and an acyl amino ring at the acyl amino side chain at C6 position and a carboxylic group. So these are some of the important features of about the penicillin. So when we talk about the acyl amino side chain at the C6 position, this is mainly essential for the antibacterial activity. So different substitutions at this position modify the pharmacological properties of penicillin. And when we talk about this beta-lactam ring, the beta-lactam ring is absolutely essential for activity. It is responsible for the mechanism of action, which is inhibition of bacterial cell wall synthesis. This ring is highly strained, which increases its reactivity. If the beta-lactam ring is opened, or in other words, we can say if it is hydrolyzed, antibacterial activity is completely lost. So as I have mentioned earlier, the fusion of this beta-lactam ring and the thiazolidine ring creates a bicyclic system called as pinum. This structure increases the ring strain, which enhances the antibacterial activity but reduces the stability. So at the first position, we have the sulfur atom, which is common in penicillin, and it does not have much effect in the antibacterial activity. And when we talk about the carboxylic group at the C3 position, this carboxylic acid group can be replaced with the salts of sodium. And this can be used for used to treat bacterial infections. This carboxylic acid also helps in binding of penicillin to bacterial proteins known as penicillin binding proteins. Now, at the substitutions on the C6 position, the C6 position has the amino side chain. This is most important modification site in case of penicillin. So, if there is an electron withdrawing group present at the substituents, here in case of R, if I have an electron withdrawing substituent, the electron density on the carbonyl oxygen decreases. So this protects the beta-lactam ring from acid hydrolysis, making the drug to become acid stable. Now, if the aromatic ring substitution is directly attached to the side chain instead of R, if I have a benzene substitution uh, ring, then it is directly attacked at the ortho position with a bulky group such as methoxy can provide a protection against beta lactamase enzymes. Say, for example, methicillin. It acts as the uh, blocking agent for beta lactamase enzymes to the beta lactam ring. Therefore, this drug becomes resistant to beta lactamase degradation. And when I see the substitution at the thiazolidine ring, say at the C3 position, you have the carboxylic acid group. If the carboxylic group forms esters, they act as a prodrugs. Say, for example, vampicillin. It increases the lipophilicity as well as it improves the oral absorptions. Now, at the C2 position, substitutions at the C2 position, we have a 2-dimethyl group. Okay, so one methyl group lies above the plane and the other lies below the plane. So modification of this position may sometimes improve the activity, but the dimethyl group is characteristic for most penicillins. So substitution at the position yes, which is in the first place, if the replacement of sulfur atom is taken place by oxygen atom or a methylene, can sometimes produce a broad spectrum of antibacterial activity. And substitution at N4 position, at N4, which is present at the ring junction, it plays an important role in the antibacterial activity. So the nitrogen should remain unsubstituted. Substitution may reduce antibacterial activity. So, on the other hand, other important things that we can see in case of the structural activity relationship of penicillin is the importance of beta lactam ring. So this beta-lactam ring, it produces ring strain, making the molecule less reactive, and it must have a cis configuration for proper activity. If the opening of the beta-lactam ring takes place, it will destroy the entire antibacterial actions also. So next we'll see the structural activity relationship of tetracyclines. Tetracyclines are a class of broad spectrum antibiotics which fight against gram-positive as well as gram-negative bacteria. So the most important feature of tetracycline is the presence of linearly fused tetracyclic nucleus. Here you can see a tetracyclic nucleus consisting of four six-membered rings A, B, C, D. So the important structural features include the dimethyl amino group at C4 position. Here you have a dimethyl amino group at the C4 position, which is essential for antibacterial activity. And a hydroxyl group also increases the um, polarity as well as the water solubility. The hydroxyl groups are found at the position C3, then C12, then at C10. Then ketoenol tautomerism occurs in the molecule as well as the zitterionic structure is possible due to the presence of acidic as well as the basic groups. So for tetracyclines to show antibacterial activity, a diketone system must be present and ketoenol tautomerism should occur. The dimethyl amino group at C4 must remain intact and the aromatic ring D is necessary. Phenolic hydroxyl groups are also important. Now, modification at C1 to C3 position. So, this is the C1 carbon to C3 position. We have a hydroxycarbon. These positions exhibit ketone enol tautomerism, which is a common feature in the tetracyclines. The beta diketone system present here is essential for biological activity. So, if there is a substitution at C3, then it results in the loss of antibacterial activity. And modification at C2 position, we have an amide group. So amide carbonyl group is mainly essential for antibacterial activity. Amide nitrogen plays a vital role in the antibacterial activity. And modification at C4 position, we have a dimethyl amino group. And it is mainly helpful to maintain the equilibrium between non-ionized as well as the zwitterionic forms. And when I talk about the modification at C5 position, many natural tetracyclines contain the hydrogen at C5 position. Some may also have the hydroxyl group, which is considered as a derivative. So hydrogen must be in alpha configuration for the activity. So sometimes at the C6 position, we have two alkyl groups. So it can be a methyl group or it can be a hydroxy group. So if there is a hydroxy group, it makes the molecules to be an unstable in acidic or even in basic media. Then modification in the ring D. So here in the ring D, we have the C7 carbon. So C7 carbon can be substituted by groups like halogens, nitro group, and even amino group, which increases the potency of antibacterial activity. The ring D must remain aromatic for antibacterial activity. Mainly electron withdrawing groups at C7 increases the efficacy of antibacterial activity. And substitution at C9 position, at C9, modifications will reduces the activity, and even a slight modification also will reduce the activity of towards the bacterial infections. And modification at C11, C12 and C12A, it is also essential for antibacterial activity because this region is crucial for metal ion chelation and biological activity. Here substitution leads to the loss of activity, and the special attention must be paid to the hydroxyl group at the C12A substituents, which plays a vital role in the stereochemistry towards the activity of the microorganisms. Now, moving on to the clinical applications of penicillin, the first production is oxazolin. So first we are taking an dialkyl substituted benzaldehyde. It is treated with a hydroxylamine, and a simple condensation reaction has taken place. So water is getting eliminated and you will be getting a CH double bond and OH. Now this is treated with the chlorine in the presence of chloroform. The H group is being eliminated and Cl is being substituted. And this is treated with a methyl acetoacetate group in the presence of sodium ethoxide. It creates a cyclic ring structure, which is a 5-membered ring structure. And now this is treated with sodium hydroxide in the presence of SOCl2. We'll be getting a compound where this COOCH3 group is replaced by COCl, and this is treated with 6-APA in the presence of triethylamine. The 6-APA is nothing but 6-amino penicillinic acid. So it creates a bond between this penicillinic acid and with this acid chloride. So simple HCl is being eliminated and you'll be getting the oxazolin product. And next one is clinical application of cephalosporin. The first one is cephadroxyl formation. Here we have taken the starting material as 7-amino cephalosporinic acid, which is undergoing reduction in the presence of hydrogen palladium on carbon. Here the acetoxy group at this position is being reduced and it's being converted into a methyl group. And this is treated with an silyl chloride group, which is acting as a masking agent, and this will mask the acid functionalized group. Okay, so why we are using a masking agent? Because we have different functional group here. We have an amino group, we have a keto group, and we have an acid group. So in order to selectively protect a particular functional group, we need a masking agent. So that's why we are using this masking agent, silyl chloride. So this will protect the acid group. And now this is treated with a para-hydroxy glycine, and in the presence of tertiary butyl oxycarbamate. And this calcium butyl oxycarbamate, it is also acting as a masking agent. It is mainly used to mask amino functional group rather than keto functional group. So it protects the amino functional groups, and then further it forms a bonding. A bonding is created between this NH2 as well as the acid chloride group. Now The deprotection is taken place in the presence of butanol and in the presence of trifluoroacetic acid, and you'll be getting the cephalodoxil. And moving on to the clinical applications of cephalothin and cefzolodin. So, in case of cephalothin, 7-amino cephalosporinic acid is treated with 2-thionyl acetyl chloride in the presence of triethylamine. Simple water is being eliminated, and it creates a bond between this cephalosporinic acid as well as the thionyl acid chloride. So, HCl is being eliminated. Now, again, this is will be getting a cephalothin. And in case of cephsalodin, we are taking 2-chloro, 3-oxo, 1-phenyl ethene sulfonic acid. It is treated with sodium hydroxide in the presence of sodium bicarbonate. We'll be getting a cyclic ring structures, and this is treated with an amide group, which is nothing but isonicotinamide, isoniacinamide. In the presence of potassium thiocyanide, we'll be getting the cephalodin product. So, moving on to the